Okay, so I send you a message through Moodle about preparing for the final exam. Okay, so I think it's about time to prepare because we have only about 3 more weeks, okay, even less than 3 more weeks. So basically, I want to help you to prepare for the final exam so you can have a good grade. And more importantly, you learn enough things in this class, okay? So the final exam or test 3 will cover all topics after the midterm, meaning the test 2 we did before. So basically dynamic programming. So we have 3-4 different dynamic programming problems. And we know that each of the problems will require a different algorithm, even though we use the same concept of dynamic programming, okay? And also, we will learn after the class today, starting from Thursday, we will start learning about blockchains and also little bit about the digital coins like Bitcoins, okay? So those concepts are a little bit hard. So that said, I will give some more hands-on practices for those topics. And maybe we just go over a little bit for the test, okay? Some very simple concepts. So the main focus of the test 3 or final exam is on the dynamic programming. And as I mentioned before, the concept of dynamic programming is pretty much straightforward, like we learned before. So it's a programming concept or a programming method, and how to apply the concept to a specific problem requires us to understand the problem, how to break it into smaller problems, and then how to memorize the intermediate results in order to reduce them, right? So the concepts are very similar, but how can we break the problem and how can we memorize the intermediate results are something that we have to pay attention to, okay? So last time we learned about Tower of Babylon, right? Then the question we answered last time was, how did we use the exhaustive search to solve the problem, at what complexity, right? And then we came up with a better idea by using divide and conquer and recursive algorithms, right? So I after the class on Tuesday, I worked out the ideas more concretely and also implemented all of the algorithms we discussed last time, right? And also, I updated the lecture notes on Moodle so you can see all of the new slides I added from time to time, right? So, by the way, did you follow the latest slides of the lecture notes? On Moodle, we have one link, but every time when I updated the lecture notes, I also updated that on the Google Drive so you can see it. So did you have the latest version of the slides? Anyone? Oops. Okay. I mean, every time when you click at the link, it will give you the latest one. All right, so let me remind you a little bit about what we did last time, okay? So, and then we will have a hands-on practice today so you understand how to use dynamic programming for solving the Tower of Babylon, okay? Um, all right, so let's go through it real quick. Okay, so that said, we have a number of blocks, right? With different X, Y, and Z values for the direction of the block. I used this one last time, right? And then we know that for each block, we have maximum of 6 different positions, right? Okay, 6 different positions. So we want to find out what would be the tallest tower that we can build from a given set of blocks. And when we have a block, we want to put it on another block, then the requirement is that the base, meaning the X and Y directions, have to be strictly smaller than the one that we want to place on top, right? Okay, so last time we went through the example, right? So that said, we have only one block, and then we have the size X, Y, and Z of the blocks. So from here, we will try to find out how many different positions we can have for the set of blocks we are given. So that said, we have here 6 difference, right? So 10, 20, 30, okay? And so on. So that said, we simply have one block and then we rotate it, right? And then here, and then here, and then here, and then here, right? So that said, we have up to 6 different positions. And last time we also want to sort the list here with respect to the base, meaning X and Y, right? So we sort this list, and luckily it's already sorted, right? For this input example, okay? This example 1. So after we have this, we build up the table over. Okay? So here are the results we have. So for the table over, meaning that at row I, and column J, it means that the block I, here, I is 2, right? Can be, if it's 1, it means that block I can be placed over J. Here is 0, it means that I cannot be placed over J, okay? So etc. So here we have a 1. It means that here, 3 can be placed over 1, 2, 3, 4, 5, 6, right? So it means that this one can be placed over this. Yeah, it's true, right? Because it's smaller, right? Okay, so after we have this, then we have a brute force solution, meaning that we want to have the exhaustive search, right? Exhaustive search means that we check all possible stack, okay? And then if the stack is legitimate, we find the height and then choose the tallest stack, right? So, and it's what we want to find out, right? And last time we already mentioned that this one will take us 2 power to the n, right? Because even with a stack of length n, we have n factorial possibility, right? So n factorial is just only on stack of length n. We have to check stack of length 1, length 2, length 3, right? And even with one of them, we already have exponential number of cases. So this one is not what we want to do. Okay, and recursive solution, last time we came up with the idea like this. Okay. Step 1, we find all possible position. We did before, right? Step 2, sort the block with respect to x and y. We did it for example number 1. Step 3, fill out the table over, meaning we want to know if a block I can be placed over block J. Okay, so this one we have the table over, right? And now find the tallest tower. We just have one recursive function I call tallest tower with I, right? With block I. Okay. So now tallest tower for the block I, we need to find out what is the max value of the tallest tower for block J, for J from I plus 1 to n. Remember that the set of block has been sorted, right? So the smallest one will be at position 1, and then we want to find out what will happen if block I can be placed on top of block J. If it is, then the height of the tower will be the height of the block I plus with the recursive value of tallest tower J, right? We multiply with the over Ij because if it cannot be placed, meaning over Ij is 0, right? And otherwise it will be 1, meaning that we compare this one plus with the height at I, right? Is the new values for the tallest height at block R, right? Okay. So Hi is the height of the block I. Okay, so after we have this tallest tower for all block from 1 to n, then we simply return the biggest value, right? So the question is, what would be the complexity for this algorithm? Okay, step 1. What is the complexity for step 1? Find all possible positions for the blocks. Big O1, no, the input has n blocks. Okay, you don't have one block. For this example, you have one block. But in general, you can have the set of blocks is 2, 3, or n in general. And in that case, you have what? Big O n, right? Okay. Actually, for every input block, you can have 6 different positions, right? At most. So that said, you should have here big O 6n, which is the same as big O n, right? Okay. Now, step 2, sort the block. What would be the complexity for this? Step 2. So all possible position, you have big O n, right? Sort that we can choose either quick sort or merge sort. You have n log n, right? Okay. Fill out the table over. What would be the cost? Remember that we have a table over to find out whether or not block I can be placed over or on top of block J. Okay, so what would be the cost? For step 3? Big O n square. Yeah, very good. Okay. Because you have n square, more precisely n square half, number of cells we have to check, right? And then for each of the pair, we have to compare the x and the y value. So it means that it's about 2 times n square, and it's also big O n square, right? Okay, now find the tallest tower using this recursive function. This recursive function, we have n blocks, right? And then we have to find out what would be the tallest tower in that the block I will be on top of the tower, right? So we have n block, right? So here we have n blocks, and then here is 1, 2, 3, 4, right? So we start from here, or we can start from here, either way. But for the recursive function here, we start from 1, right? And then for tallest tower I, we will check the max values of the tallest tower J, starting from the next one, right? Or more precisely, okay, we start from here. We're going to see whether or not this one can be placed on top of this, right? And then from there, we will see what would be the value of the tallest tower from here, right? And then from here, and then from here. Right? So that said, if we calculate this, okay, it will be a recursive call for checking this cell, and then this cells, and then this cell. Okay, remember that the cells on the left has the smallest base, right? So whether or not it can be put over the next one, and then we call the recursive function tallest tower for the next, right? Okay, etc. And then you can ask, here is the recursive function, right? But recursive function here, we call it 1, and then invoke it with 2, with 3, then what would be the base case? Usually we have the recursive function, right? The base case will be the smallest value of I. But in this case, the base case would be at the biggest one, because at the biggest one, we cannot put it on top of anything, right? So that said, when we reach the value where we have the block with the biggest value, with the biggest base, right? Then return value of tallest tower of 4 would be the height of that block, right? Meaning the Z value. Okay, so what would be the complexity for this step? remember that we have here the recursive function. Can you pull out a piece of paper and try to find what would be the complexity for this? Okay, I'll give you about, say, 2 minutes, okay? Now, use all of the method you already learned for calculating the complexity of a recursive function, right? I mean, in the first part of the class. Now, try to find out for this recursive method, what would be Tn? Okay, so anyone? So first, we will try to have Tn, right, in terms of the smaller t, like Tn minus 1, Tn minus 2, etc., right? So from this pseudocode for the recursive function, okay, how can we find out what is Tn in terms of the smaller values for t? And once we have the recurrence, then we can solve it, right? Using the methods you learned before, like back substitution or recurrence tree, etc., right? Okay, so let me remove this one so we can write it here a little bit. So from here, you can see that, okay, Tn would be the total cost for this tallest tower, right? Meaning that Tn, in order to find out Tn, we need to call the tallest tower for I from 1 to n, meaning that we call the tallest tower for 1, for 2, for 3, until n, right? Where n is the number of different positioned block, right? So that said, here you have Tn is by calling at least you have 1 to n, right? And then for each of T1 and T2, T3, etc., right? We have to find out the max again, right? of every node below that position. So at least Tn will be less than or equal the sum of Ti for I from 1 to n minus 1, right? Even more, but at least we have Tn is smaller than this one, right? Okay? So, or roughly speaking, is about the same, right? So we can have it here. Oops. Okay. Now we have Tn is similar to the sum of Ti for I from 1 to n minus 1. Okay. Then how can we solve that? We have Tn on the left-hand side and sum of Ti on the right-hand side, right? Remember how we calculate the average value for quicksort, right? So that said, we have Tn here, replace n by n minus 1. And then here on the right-hand side, we have Ti for I from 1 to n minus 2. Subtract both sides. Then we have Tn minus 1 on the left-hand side and Tn minus 1 on the right-hand side. Move Tn minus 1 to the right-hand side, then we have Tn is similar to 2 times Tn minus 1, right? Okay? And if it's the case, then we already know that Tn would be at least 2 power to the n. Okay, so here's what we have, right? So Tn here is big O of 2 power to the n when we use the recursive function, right? Okay? So once we know the recurrence, right? Here on the right-hand side, we have the sum involved. Then we remember about how we remove the sum when we solve the recurrence, right? It's what we did for, say, quicksort analysis, right? And then here we can use the same. Okay, so that is about recursive. And then for the dynamic programming, we use the same step 1, same step 2, right? Same step 3, step 4. The difference is that we don't have the recursive function, but we find the tonneless by memorizing the array dp, right? And here we will do a little bit different. It's from bottom up or from right to left, right? So that said, dpi, when we calculate it from right to left, we will try to remember the values, right? So checking whether or not a block can be placed on top of the other. If it's the case, then add the height into the dp value of the previous values, right? And then we return the dp. Okay, so the algorithm is here. And last time we practiced, last time I went through this example. Okay, so again, here we have the size is 1. I mean, the number of blocks is 1. The size of that block is here. So we follow step 1, right? Step 2. Step 2, we don't have to do anything here because this list is already sorted. So step 2, we don't need to do anything. Step 3, fill up the over table, right? So we fill it up like this, right? And after we did it, we just have the DP table. The DP table, what we did was that we will try to calculate DP from right to left, right? So meaning that the last one here corresponds with this block, right? So that said, we do bottom up. Or in other words, when I write here, because I don't have enough space, then I will have to go from right to left, meaning that I will follow this list bottom up. Yeah. So first, the last DP value will be simply this value, right? The height or the Z value of this block. Yeah, so here's the Z value. And here's the X value. Here's the Y value, right? Okay. So now I start with this. I just want to know whether or not this block can be put on the bigger one on the right-hand side. Or in other words, if I'm working at this block, I want to see if this one can be put on top of the bigger one, meaning below that, right? So for this one, I just, let me write here, 1, 2, 3, 4, 5, 6, right? It corresponds with 1, 2, 3, 4, 5, 6. Okay. 5. We want to know whether or not 5 can be put on top of this. Okay. Here we have again 5, 4, 3, 2. Right. So here 5 cannot be put on top of that. So that said, the value I have here for DP is simply this one, right? So for the 4, same thing. Okay, I have 10, right? Now for the 3, okay, for the 3 here, I know that it can be put on top of the last one, right? So that said, I will see here 3, I have 30, and then on top of the last one, I add this 2, and then I have 40 here, right? There's only one possibility that 3 is on top of 6. So the max one is the only possible situation here, right? But if we have many 1 here, it's a different story. We have to go through each of the cases, add the value together, right? And then find out where we have the biggest one. Then we will put the biggest one here, right? Okay. So similarly, for this one, we have only one situation that 1 can be put on top of 4, right? So that said, we have D4 is 10, right? So DP1 is 30, and then we add with, so 4, DP4 is 10, right? So we add this one, and then put it here, right? So after we are done, we just select the biggest value on the DP, and this the tallest height of the tower, right? So there are 2 different ways we can use for building the tower. One is here, and one is here, right? So we can just simply print out 40. Yeah. If we have to print out the whole tower, then we have to remember, right? One more thing, that is the place, right? We can modify the algorithm here to list the whole tower, which one on top of which one, in order to have the tallest height, right? But that algorithm can be modified, and we already know how to did it for matrix multiplication, etc., right? Or the assembly line, or the longest common subsequence that we already learned how to list the actual result instead of simply the tallest height of the tower. Okay, so that is the algorithm that we discussed last time. So today we will practice. We have a hands-on practice on one particular example to see how we can use the algorithm we have here to find out what is the tallest height of a Tower of Babylon we can build based upon a given set of blocks or blocks input, right? Okay, so here is what we will do today. Yeah. And by the way, the recursive solution we already know, and then we have the complexity for the dynamic programming. Okay? Everything could be the same, right? For step 1, step 2, and step 3, but for the dynamic programming, because we memorize and fill up the array bottom up, then the complexity would be n squared, right? Because when we go for each value of the DP array, so here's the DP array. Okay. We go from right to left, right? So for each of the value here, for example, when we are here at this place, so we have to go through n cells, right? N cell. For each of the cell, what we have to do is that we have to look up the table over, right? If the value is 1, then we add the height at I plus with the dj value, right? Meaning that we will try to see from the cells below the current cell to see if this one can be placed over this one. Then we add the tallest height of the tower with this cell on top of the stack to the values here, right? So that's said for every cells, we have to look back at most n values, right? More precisely, when we have the first place here, then we have to check n minus 1. This one we check n minus 2. This one we check n minus 3, etc. Right? So that said, we have the total number of steps would be big O n squared, right? Because for each of the cell on the DP array, we have to check n minus 1, n minus 2, n minus 3, etc. Right? So that said, this one will take us big O n squared. So in general, the total number of complexity for this dynamic programming is big O n squared, right? So that is what we have for the complexity. And so we know that dynamic programming is many times more efficient than either exhaustive search or the divide and conquer recursive algorithm. All right, that is the complexity. And now we have the hands-on practice for the rest of today. So we have two blocks with this size. Okay? Now, tell me what would be the tallest height of the Tower of Babylon? If you forgot about the algorithm I just reminded you, you can just open the lecture notes, right? Just click on the link of lecture note 9, L9 for dynamic programming. You would have the latest set of slides, including the algorithm I just reminded you. Okay? So we will try to spend about 15 minutes. I think you can do it in 15 minutes because here from this one, I already know that you have about 6 different type of blocks. So a matrix or an array of 6 by 6 can be filled in about 10 minutes. Okay, so I'll give you 15 minutes to work out this hands-on practice, and then I will go through the solution with you. Okay, pull out a piece of paper and try to work on this hands-on practice as much as you can. Okay, so anyone who has the tallest hay, just time in the number 51. Okay, very good. All right. So how about the other ones? Brian, have you done yet? Jared? Okay, very good. And John, you have 51. Brian Jacobs. Okay. Where are you now on the problem? Do you need a few more minutes? Okay. Then I mean, we don't want to wait anymore, right? So I will go through the solutions and then we'll discuss with you. So three of you did it very well. So here are what we have. And by the way, I implemented on the ideas we discussed about last time and have it in the software package here. All right, so Zoom Fighter 400, and let's just have it here. Okay, so let me run through this one. Okay, so here's the Tower of Babylon we have, right? And the implementation is just what we discussed in the class, right? All right. So let's see what we have here. So on the inputs we have on the question sheet here, so it's correct. Okay, so now we have this one. All right, 51, very good. Okay, I have to run the program first. Okay, and now we have this one. Okay, 51. All right, very good. So 10, 20, 10, 10. Okay, so that is what we have for the input. Let me double check to see if we actually have it that way. Yeah, 20, 10, 10, 20, 31, 20. Okay, so it's actually what we have. Okay, now let's go through the steps, right? And by the way, I have a simple program that can generate a lot of inputs that I want. Okay, for example, I want to have how many position blocks, right? So for example, in this case, I just want to have 6, right? But I can generate examples in that I have 8, right? Etc. And I can also generate the example in that how many of the one I have on the over table. Okay, so I can control the number of say calculation you have to put in for any particular example. Okay, so here's what we have, and you can check it with your result. So here are the number of blocks we have in different positions, right? 1, 2, 3, 4, 5, 6. And it's already sorted, right? Did you have the same? Okay, very good. And then here are what we have, right? I just list them in one place. And now we have the over table. So the over table here you have, now see that below the main diagonal, I have the question mark here. It means that I don't have to calculate them. Okay, I just leave it blank. So let's see what I have here. Do you have the same? We just have 1, 2, 3, 4, 5. Okay, excellent. So you have the same, right? And now once we have this, and then we can fill in the dp value. So the dp values are here. Okay. So starting from the 6, we go to the left, right? So the first one we have is 20. And now when we go to the position number 5, we also have 20. And then we have 31, 30, depending on here, number 5, we have all of them 0. So it will be simply the height of block 5, right? Okay. And then 4, same thing, is the height of block 4. 3, we can put it on top of 6. So that means that 3, we would have it 10, and then plus the one on top of 6 is 20, right? So 10 plus 20 is 30. Okay, so do you have the same thing here? Okay, very good. So you have 51, 30, 30, 31, 20, and 20. Okay. So is what we have, right? Okay, excellent. Looks like I mean, you got the idea of this dynamic programming algorithm, right? So remember that we just have to go from right to left, and then remember the value here, here, and then whenever we calculate the value at 2, we just use the previous value. We don't recalculate them. Okay. So looks like at the beginning we have the problem. It looks like it's complicated, right? But once we analyze it, we can design the algorithm that can solve the problem here efficiently, right? Okay, so let's go back to what we have before. That is the superhuman. Okay. Just go to page number 1. Okay, so that's it for dynamic programming. So we learn 4 different problems in that we design our dynamic programming algorithms, right? Number 1, that is how to multiply a chain of matrices. Number 2, how to, let's say, find out the best way for an assembly line for the cars. And then number 3, finding the longest common subsequence. And then number 3, finding the tallest tower of Babylon based upon a given set of blocks, right? Building blocks. So out of these 4 problems, I think we spend a lot of time for practicing, right? Now, I will give you one homework assignment that I will post on Thursday, hopefully before the class on Thursday. And in that, for each of the dynamic programming, I will give you one hands-on practice. And you have to solve all of them and submit the solution. And that will be used for preparing you for the final exam, okay? Now, out of these 4 problems, which one you want to practice more, or you feel that you are comfortable with all of them? Okay, very good. How about the other students? John, Jared, Martin, and Brian. Okay. How about you, Brian? Okay. Oh, okay. So that said, you may want to view the lecture videos I posted already, right? And then try to do the hands-on practice we have today. Okay, try to finish it by yourself. Okay, and hopefully after you can finish the hands-on practice today by yourself, you will feel more comfortable. Okay, very good. So we can start learning about blockchains from Thursday. So I just want to ask you if you learned anything about cryptography before, let's say in the CMPS 390 algorithms. Did you know anything about, say, public keys, private key? Okay, then I will start from scratch. Okay, so if you learned it before, then I can skip some of the basic things. But looks like 329, yeah, but probably a little bit, yeah. So okay, at least did you learn about the algorithm there for how to build up the public key and how the algorithm for encryption or decryption? No. Okay, then I will go into the details for that, because those things, even though it can be used for computer networks, but it will be used for blockchains as well. Okay, very good. So looks like we are a little bit early today, but I will let you go. Okay, so I think we have enough thing to do today, and you did very well for the hands-on practice. Any question? No question? Okay, then that's it for today. Take care and bye-bye.